Unit 3 review. All right, well, for Unit 3, we have a few kind of big topics that we really covered, and that'll kind of be the basis of our review. The first topic that we covered really was energy and work, followed by power. After power, we really talked a lot about springs and some of the characteristics of springs. Then we go on to momentum and the conservation of momentum. And finally, impulse. So when we went through and created this test, we really thought about questions that would fall under these 5 categories. Also, this will be the first test where you will also see just a few questions from prior units. Questions from old units. The questions from prior units, anything's going to be fair game. You may see something along the lines of a force question or a question involving velocity or speed. You also may see a couple questions on projectiles. And again, we're thinking of the conceptually based projectile problems, the conceptual force problems, and different concepts like that. So let's do just a small summary of each of these 1, 2, 3, 4, 5 topics, and that'll be our review. First, let's start off with energy and work. Well, remember that energy is going to be the ability to do work, and that energy falls into 2 categories, potential energy and kinetic energy. And we know that our potential energy is mgh, and our kinetic energy is 1/2 mv squared. It's important to note that energy is not a vector quantity, not a vector. That means that direction is not so important. When we're talking about energy, magnitude is more important, the amount of energy. Well, that brings us to work. Work is really going to be when a force makes an object move. So remember we said that energy is the ability to do work, and work is going to be when a force makes an object move. Some people also think about work as a change in energy. So if I have a change in energy, I know that work is being done. Work is going to be force times distance, and this also is not a vector quantity. Now, I wish I could tell you that you didn't have to memorize any equations for the conceptual multiple choice part of the test, but quite honestly, these 3 equations are equations that you should feel comfortable using and comfortable knowing. So I think they're 3 kind of very comfortable equations, and unfortunately, yes, you will need to know these, not only for the test, but also for the actual AP exam in May. Let's pull up a new slide and talk about power. Power is the rate of energy transfer. The equation for power is work divided by time. Now remember that work itself can then be broken down into force times distance. So really you can also think about power as a change force times distance, and sorry to use a d there and an x there. Hopefully you can handle that. Force times distance divided by time. So these 2 equations really kind of give us the idea of power. Now power also is not a vector quantity. Not a vector. Oops. Huge C there. And of all 5 of these topics, power seems to be the one that is least covered in our textbooks, in practice tests that I've seen. And so it's one that I just don't think is as crucial as maybe energy or work or conservation of momentum. And I think it's because really, if you think about it, power is kind of a one-trick pony. It's the rate at which work is done. So I'm really limited on the types of questions that I can actually do with power. Not to say that you shouldn't really kind of feel comfortable with these equations, but that I just wouldn't spend as much time on power as I might on like conservation of momentum or impulse. Let's move on to a new slide and talk about springs. So now when we're talking about springs, remember that springs can happen in two ways. They can be vertical springs or they can be a horizontal spring. In both situations, really what's important is to know that the x value is going to be the length of or is going to be the distance that the spring is pulled away from the equilibrium point. And because the x represents the distance from the equilibrium, these values are going to be considered vectors because we're going to either be compressing our spring upward, and so it'll be either a positive or negative number depending on how you decide to make it, or we'll be stretching the string. And so you'll have kind of your baseline, and then as you compress or stretch the spring, you'll be talking about two separate directions. As a result, you'll be talking about a vector. A direction matters for these type of examples. Another equation that's very important that you're definitely going to have to feel very comfortable with for the conceptual portion of the test is going to be the spring constant equation. In order to find the spring constant, you take the force acting on the spring and you divide it by the distance. Now, again, now that we're thinking about force, you have to really think about if you're talking about a horizontal or a vertical spring. If you're talking about a vertical spring, force is going to be the mass times gravity. If you're talking about a horizontal spring, force is going to be something different. Now this could be maybe possibly force applied, this could be force as a result of something hitting it, like a collision, and the question will specify that. But just keep those in mind that for a vertical spring, the force is going to be mass times gravity, and for a horizontal spring, we're going to have a different scenario for the force. When I'm thinking about the potential and the kinetic energy for our spring, the kinetic energy is the same, 1/2 mv squared, but the potential energy of a spring is a little bit different. When we think about a spring's potential energy, we're going to have 1/2 multiplied by the spring constant, multiplied by the distance from the equilibrium squared. And remember that the kinetic energy is going to be equal to the potential energy of the spring according to our law of conservation of energy. So you may, based on these equations here, may have to solve for, you may have to solve for velocity, you might have to solve for the spring constant, you might have to solve for mass. It's unlikely that you'll have to solve for the distance pulled away, but you might. I think the big ones are going to be these first three. If you can comfortably solve for these first three values using the K equals US equation, using the potential energy is equal to the kinetic energy equation, you're in good shape. Let's move on to momentum. Momentum is going to be a product of an object's mass and its velocity. When we're talking about conservation of momentum, we need to realize that this is a vector quantity. Hi, Mr. Culligan. And that our equation for momentum, another one that you're going to have to feel very comfortable using on a multiple choice, thus maybe having to memorize, is going to be mass times velocity. So for our momentum, we're thinking about mass times velocity. Now what's really big here is going to be the conservation momentum. We have the conservation of momentum, which is going to be the mass of object 1 multiplied by the velocity of object 1 plus the mass of object 2 multiplied by the velocity of object 2, and this is all going to be equal to this being before a collision takes place. The momentum before must be equal to the momentum after. So our masses most likely are going to stay the same. However, our velocities could change. So we could have a new velocity for each object after. And remember that if the objects stick together, that means that they will have the same mass. So if we have an inelastic or an elastic collision, elastic meaning they bounce, so this up here would be an elastic situation. If they stick together, however, we can just simply take the masses and add them and then multiply by their shared final velocity. We'll just say VF here. And this would be for an inelastic collision. Now, the big thing with the conservation of momentum problems is you just have to kind of think about, is it in one dimension or two dimension? Most of the problems we'll see are going to be in one dimension. You may have one or two in two dimension. And if those problems are in the two dimension, and let's just scroll down a little bit, if we're talking about a two-dimensional problem, you just need to make sure that you consider the like horizontal and the vertical components. So you'll have a vertical or a y value for your mass 1 multiplied by your velocity plus your mass 2 multiplied by its velocity is equal to your second mass, your first mass by its final velocity. Sorry, this is rushing now and I shouldn't be. So those are for befores, plus your mass 2 and its final velocity. All of those being in the y component, and then you'll need to do the same thing for the x component. Same kind of equation down here. You definitely don't want to hear me try to repeat that whole thing one more time. Hopefully that's comfortable in the idea of the two-dimensional conservation of momentum. All right, last thing, impulse. Let's pull up a new slide. So when we think about impulse, we can think about it as a change in momentum. We can also think about it, however, as just really the product of a force and the time interval that that force is being applied. So this kind of has two different ways when we're thinking about it. The impulse equation is going to be our force multiplied by our change in time, which remember is also going to be equal to our change in momentum. The change in momentum equation is going to be a change in velocity multiplied by the mass of the object. There's spectators in the room now. Impulse is a vector quantity, That means direction does matter. So for whenever we're thinking about impulse, we want to think about it is a vector quantity. Finally, the last thing with impulse is you may see a graph. You may see a graph in which you are comparing the force of an object and the time that that force is applied. In order to calculate the impulse or the change in momentum, all you'll have to do is find the area under that line. That area under that line will give you the impulse or give you the change in momentum. And as a result, you may have to solve for things like the mass of the object, or maybe the change in velocity, or maybe like the velocity final in these types of situations, given the force and time graph and the area under that curve. And remember, the area under that curve will give you the impulse, also known as the change in momentum. All right, that's all for this unit and all for this review video. Have a great day.